Thank you, Aaron, and thank you for coming back for part two. I was going to put a recap here of part one, just so we all have a running start at what I want to do today. So the one-sentence summary of yesterday's talk is, if R is a complete, and this is the important word in this sentence, complete local ring, then it satisfies the Kroll-Rimac-Schmidt property. In other words, direct sum decompositions of finitely generated modules are essentially unique up to permuting the factors. And today, I want to discuss how bad can it get for non-complete rings? So, for example, here are some questions to guide us. Could we have, let's say, indecomposables A and B and C and D, so that A direct sum B is isomorphic to C direct sum D, but not any of the pairwise ones? Obviously, yes, because this is an essential. If this never happened, then all of the rings would satisfy Kroll-Schmidt. Could we have slightly worse? Could we have A plus B isomorphic to C plus D plus E? Again, indecomposables. So here I'm saying that the number of indecomposable summands on each side is different. Could we have indecomposables A and B so that two copies of A is isomorphic to three copies of B? Could we have, I had a couple more I wanted to mention. Could we have A indecomposable so that A is indecomposable, a direct sum of two copies of A, a direct sum of three copies of A, and so on up to, say, a direct sum of 72 copies of A, so that these all have only the expected decompositions. These all have only these decompositions as written. But when you get to 73, that decomposes into, say, indecomposables. Or finally, one last one to guide us, could we have infinitely many indecomposables? Let's call them, say, AI, so that AI divides M for all I. Remember, this is my notation for is isomorphic to a direct summand of. So these are all possible descriptions of failure of Kroll-Schmidt. And the interesting thing is that some of them can happen and some of them can't, and it's not 100% clear from the beginning, which ones are worse. So just for example, I'll say, how about some colored chalk? This one, obviously, we said yes. This one, yes. This one, no, this one can't happen. Though you wouldn't think to look at it that it looks any worse than one of these. This one, yes, this terrible thing can happen, but this one, no. So let's discuss what structure is in place that allows the yeses and prevents the nos. So our strategy for this is to compare mod R and mod R hat, where, so set the notation for the rest of the day, the rest of the lecture. Rm is a local ring, Noetherian always, with M-adic completion, R hat. This is an obvious thing to do since we understand the module theory over the complete local ring. Additionally, we're going to use the semigroup structure on these two module classes, categories. So what do I mean by module structure, or semigroup structure? So you can define m plus n, well, to be just m plus n. So we add, I'm going to be very sloppy, I guess, about isomorphism classes of modules versus the actual modules themselves, and when we think of this as a category versus when we think of it as a semigroup. It will always be a semigroup, is the short version. So, sure I don't leave anything out. Yeah. Some first observations. The first is, as a semigroup, mod R hat is free. It has no relations. Specifically, it has a basis consisting of the indecomposable modules. So another way to write that is that mod R hat is isomorphic as a semigroup to the natural numbers, some huge direct sum of copies of the natural numbers, indexed by, so the index set I consists of isomorphism classes of indecomposables. Secondly, the natural map from mod R to mod R hat, where you just take a module and complete it, or if you prefer, tensor with the completion, same thing, is a semigroup homomorphism. That's just to say that M direct sum n hat is isomorphic to the direct sum of the hats. So that's not complicated. Third, if you complete two modules and they become isomorphic upstairs over R hat, then they were isomorphic before. This is a version of faithfully flat descent, I think probably first in EGA, maybe. Also, there's a very nice proof due to Bob Guralnick. So in particular, that means this map is injective. But it's actually better than that. It's what's called a divisor homomorphism. Of semigroups, which let me tell you what that is. Oh, whoops, I left one out. Well, I'll come back. It's a divisor homomorphism of semigroups, meaning if M direct sum, no, let me write it like this, sorry. If M hat divides N hat, that is, after passing to the completion, M is isomorphic to a direct summand of N, then M was already a direct summand of N. And this, in fact, is in the same place. And finally, as a last preliminary fact, in particular, mod R is what's called a cancellative semigroup. So if M direct sum X is isomorphic to M direct sum Y, then insert here a short proof, which I won't write down, pass to the completion, use the fact that you can cancel over the completion with the Kroll-Schmidt property over the completion, and then descend back down, then X was isomorphic to Y. So this semigroup homomorphism from mod R into a free one is not just any old homomorphism, it's a very particular kind. And this already allows us to rule out one of the kinds of bad behavior. We cannot have this sort of behavior. 2 copies of A isomorphic to 3 copies of B for indecomposables. A and B. So let's talk about why. If we had this, then of course we get the same thing with hats. And this is happening in mod R hat. Sorry, Dale, is that in the way? Which, remember, we can think of as just vectors of natural numbers. Well, vectors indexed by some probably enormous index set. But as such, it has a natural partial order. In the component-wise partial order, two copies of this one is equal to 3 copies of that one. That means this one must be bigger in every component. So I warned you that I was going to be sloppy and go back and forth between module categories and semigroups. This is a thing that makes no sense, of course, for modules, but in that free semigroup it makes sense. Every component of A hat is bigger than every component of B hat. But in a free semigroup with a basis, this means we must have divisibility. Hat must be isomorphic to a direct summand of A hat. And then we can descend. Oops, there we go. If B hat is a summand of A hat, then B is a summand of A, but they're both indecomposable. So B is isomorphic to A. And this equation then says 2 copies of A isomorphic to 3 copies of A. But we can cancel. I'll put it up here. And so A had to be 0, which I guess maybe 0 is indecomposable, so that qualifies. All right. So I said, in general, this index set I is enormous, probably uncountable, maybe even worse. To localize the problem, to make the problem smaller and more manageable, let's consider a single module. And I think Jan used this notation yesterday. Add M with a lowercase. All of my categories are lowercase categories. So this is the direct summands of direct sums of copies of M. Then, of course, we get the restriction of our semigroup map restricts to a map of these semigroups. Add M, of course it's still a semigroup. Take any two things in there and add together, you get another one. But this, what is this? Over the completion, we have Kroll-Schmidt. This is a direct sum of indecomposables in a unique way. So this is a free semigroup of finite rank. So to summarize, this add M admits a divisor homomorphism. It's the restriction of a divisor homomorphism into a free semigroup of finite rank. Now again, this already rules out another possibility. So let me explain what that is. Maybe I'll call this a proposition, which is that add M contains only finitely many indecomposables. So the last possible behavior that I mentioned was infinitely many indecomposables dividing M. This can't happen. In particular, M itself has only finitely many direct sum decompositions. Now, I thought I might prove this, but let me just give a sketch which points out the essential result that you use to prove this. So to be, so I guess it's actually, it's literally true as I've written it, though a little bit dumb. What you probably should say is only finitely many decompositions up to permuting the factors. But if there are only finitely many up to permuting the factors, there are only finitely many permutations, so it's the same. It's a different number, but it's the same. So let's just consider add M, just to consider it as a sub-semigroup of n to the n. And if we have some, let's say, L in add M, so this means L is a summand of a direct sum of copies of M. Let's write L equals, this is terrible, terrible notation, you should never do this. L is a vector of length n. Now, we again use the component-wise partial order, on this free semigroup, and observe that if L is indecomposable, then this vector is a minimal element of the subsemigroup ad M. This is by the cancellation property, and vice versa. That if you have a minimal element, it must be indecomposable. That's probably even easier to see. So indecomposables correspond to, or are, minimal elements of this subsemigroup, and now we use Dixon's lemma, which says a subsemigroup, well, this is the case of Dixon's lemma I need, a subsemigroup of a free semigroup has only finitely many what are called clutters. And I'll define that. That is subsets having no comparable elements. Is that what I mean? Every clutter is, yes, that is what I mean. That's not what I've written though, is it? Thanks, let's try to fix that. Yeah, so the sentence got kind of marbled. I meant to say a clutter in a subsemigroup. Everybody, no, that didn't work. Let's try again. Sorry. Says that a clutter, which again is a subset with no comparable elements, in a subsemigroup of a free one, is free, or is finite. So since we know that indecomposables match with minimal elements, you can have only finitely many minimal elements by Dixon's lemma. They form a clutter. And so you have only finitely many indecomposables. And that's the proof. Thanks for the assist. So what we've seen so far is that this semigroup point of view puts fairly strict conditions on ad M and on mod R. So the fact that mod R, that's the big one, and ad M, that's the small finite one, are, this is a word I learned this morning at breakfast, divisor closed subsemigroups of a free semigroup, or of two different free semigroups. Divisor closed means they admit a divisor homomorphism into the free one. Puts restrictions on the awfulness that they can attain. But there are still some pretty bad semigroups out there, even divisor closed ones. So let's look at an example of a slightly bad one. So let's look, so we're leaving commutative algebra for a moment and just talk about semigroups. So let's look at S for semigroup. Let's think of it as column vectors of natural numbers so that, let me make sure I get the equation correct. 72x plus y is equal to 73z. Then I'll leave it to you to check that this inclusion of S into N3 is a divisor homomorphism. So this is a divisor closed subsemigroup. Then what are the minimal elements? Well, there's one sort of obvious one. There's 1, 1, 1. Then there's, I'll do them in the right order so I don't get muddled later. There's 0, 73, 1. And there is 73, 0, 72. And maybe we call these A, B, and C. Then A is minimal. 2 copies of A, well, that's just A plus A. That's the only way to write this in terms of the minimal elements. 3 copies of A. Also, that's the only way to write this in terms of the minimal elements. 72 copies of A. That's the only way to write this, but 73A, if I've done this correct, is B plus C. So this should be reminiscent of one of the questions we asked at the beginning. Can you have behavior kind of like this for modules? Can you have an indecomposable so that you take direct sums of it with itself, you get only the expected decompositions until some point something bad happens? And what we see now is that at least the semigroup structure doesn't rule that out. But what we don't know yet is whether this can actually be realized. Can this semigroup, or any other, be realized as, well, either mod R or add M for some ring and some module m. And that's the last thing I'll discuss today. And I'll continue discussing it tomorrow, I believe. I don't think I'll get close to done today. Modi said we shouldn't keep the audience in suspense, so I'll just... Yes. Yes, we can. Even over a one-dimensional domain R. So you can build a ring R and a module M to reflect this behavior, and you don't even have to build a very big, complicated ring. Well, it's a little complicated, but it's not very big. So to discuss why this is true, there are two main ingredients. First, we need to control which R hat modules are extended from R. And let me say just a little more before this is too vague to be useful. So, I mean, the behavior of their ranks after localizing at minimal primes. Of our hat. Holds the key. And step two, once you've done that, is to build modules with very weird behavior at the minimal primes. And if you can do that, you can realize these semigroups. So let me now I'll go ahead and state a more precise version of 1, and that will probably be it for today. So 1 is a theorem, a beautiful theorem of Larry Levy. Oh, whoops, now I've said Larry. Now I have to remember what Odenthal's first name is. Charlie. Thank you. I don't know, can I call him Charlie? I've never met him. Sure. Okay. So, it goes like this. This is from, I learned at a meeting 2 weeks ago in Toronto in honor of Ragnar Buchweitz that I don't know why he and I never discussed this, but he was adamant that referring to a year in this format is ridiculous. Hilbert proved things in 1896. Which one are you talking about? Be specific. Larry Levy wasn't that old, but sort of close. So it says this. Let's let Rm be a one-dimensional, as I foretold, one-dimensional local ring such that R hat is a reduced ring. Then a finitely generated R hat module, let's call it N, is extended from R, that is, isomorphic to the completion of some M, if and only if when we localize N, so this is going to happen for all P minimal prime of R hat, when we localize N at a minimal prime of R hat, that localization is a field because our ring is reduced, and we just look at the vector space dimension. But this is equal to the same quantity for all P and Q such that their intersections to R are equal. So they lie over the same minimal prime of the little ring downstairs. And as a consequence, and this will be the last thing I say today, if we are able to build a domain, which I said we were, then all of these intersections down to R are the zero ideal. So this condition has no content. So this says that N is extended if and only if N has constant rank. That is, these vector space dimensions are always equal. So as I said, this will be the last thing I say. I'm pretty sure that Nick Baith is going to talk a lot more about the result of Levy and Odenthal and generalizations in his talk on tomorrow. So come back for more of that. And in my third talk, I will show how to finish part 2 of our strategy, which is to build a bad ring to which to apply the theorem of Levy and Odenthal. So thanks for your... yeah, minimal primes, sorry. Thanks. Okay, that's it. Thank you. Yeah, sorry.